Welcome to this video about geometric sequences. What exactly is a geometric sequence? Have a look at those circles. Let's suppose the area of the large circle is 1. Each time we are halving the area. So we have a half, a quarter, and so on. And these are actually drawn to scale. They represent a geometric sequence of numbers, in this case in terms of the area of a circle. And we can represent it, as you can see there on the screen, as a sequence. 1, a half, a quarter, and so on. To be more precise, we can say that a geometric sequence consists of a set of numbers, which we can call terms. And there's an example, a different one this time. We have the sequence 1, 2, 4, 8, 16, and so on. The numbers are doubling, aren't they? And the first term we represent by the letter A, or T1 to mean term 1, and term 2 would be T2, and so on. And what we notice is that each successive term is obtained by multiplying the previous term by the same number or value, which we call the common ratio, and we use the letter R to represent that. So for this example, we have that R is equal to 2. We are doubling each number. And to work it out, if you're not sure about that, all you do is take any two consecutive terms and divide the second term by the first term. As you can see there at the bottom, R will be 4 divided by 2, which is 2, or if I take the consecutive terms 8 and 16, R would be 16 divided by 8, which is also 2. We can generalize that. The nth term in a geometric sequence, we have our 4 terms there. The first term we can represent by the letter A, as we saw in the previous screen. Remember that to obtain each term we multiply by the common ratio, which is R, so that term 2 would be term 1 times R, or A times R. Term 3 would be the second term multiplied by the common ratio R. And for term 4, you can see there we multiply by R again. Now we can simplify those or write them in a different way. A I can write as A times R to the power of 0, because R to the power of 0 is 1. A times R I can write as A times R to the power of 1, and so on. What I'm trying to do is obtain powers of R. And now for the general nth term, you can see that we can write that as Tn, and underneath that A times R to the power of n minus 1. It's n minus 1 because you can see that the subscript of each t term is always 1 more than the power of R, or in other words, the power of R is always 1 less than the subscript of the t. So we can just write our general Tn formula for the geometric sequence as Tn equals A times R to the power of n minus 1. That allows us to work out any term of a sequence if we are given the value of A and the common ratio R. Let's try an example. You have a rich uncle who gives you $999,999 for your birthday. He didn't want to give you an extra dollar in case it went to your head. Now, each year you've decided that you will be spending exactly 1/3 of that amount that you spent in the previous year. Can you work out how much you will be spending during the 7th year? We can do it this way, I suppose. The first year we start with that amount that you were given. The second year you will be spending 1/3 of 999,000 and so on, which is $333,333. The following year it will be 1/3 of 1/3, and so on. And for the 7th year, if you continue with that process, you can see that it will be 1/3 of 1/3 of 1/3 of 1/3 of 1/3 of 1/3 of the original amount. Now we can use a faster method to do that using a geometric sequence. There's our formula. We know that the first term will be 999,999, and we know that our common ratio will be 1/3. As you can see from the left, when we worked out that each term, or each year in this case, we're working out 1/3 of the previous year. Substituting those two values in our formula, we have with n equals 7, because we are working out the 7th year. You can see what we have there, and working that out, it comes out at about $1,371.74. Now, what is a geometric series? We know what a sequence comprises. A geometric series really is nothing more than having plus or minus between the terms. In other words, we are summing the terms. So let's suppose we have this geometric sequence. Common ratio is r equals 2 because we are doubling the values. You can see that add the values, add the terms. We can write it as 1 plus 2 plus 4 and so on. Here's another example. We start with a geometric sequence, minus 100, minus 20, and so on. R is a fifth because to obtain each term we are multiplying by a fifth. And as a series, we can represent it as you can see. The third example, 27 minus 9, 3. In this case, you can see that the terms are alternating in terms of sign, plus, minus, plus, and so on. So to make allowance for that, the common ratio will be negative a third. We are multiplying by a negative. And to show that as a series, you can see that we have 27 minus 9 plus 3 and so on. We can obtain a formula for the sum of a geometric series just as we have a formula for the nth term of a geometric sequence. Now this is the derivation. Let's suppose the sum is represented by Sn, as you can see there. And what I've done is shown the sum of each term, A plus AR and so on, all the way to the nth term. We multiply both sides of the equation by the constant ratio R, and it becomes, as you can see there on the left, R times Sn equals, and each term on the right is being multiplied by R to obtain the new terms. Now let's match them. The Sn in the original is matched with Rsn. The A in the original doesn't have a match, so it's on its own. But the other ones you can see have the same terms, the same powers, except for the last term of the second form. If I subtract the second expression from the first one, you can see what's happened. All the in-between terms cancel except for the first term A of the first series and the last term AR to the power of n of the second series. And we have what's left. Sn minus Rsn equals A minus AR to the power of n. We can take out a factor of Sn from the left-hand side and also a factor of A from the right-hand side, and we obtain the expression that you can see. And then Sn will be A bracket up 1 minus R to the n over 1 minus R. And that's our formula for working out the sum of a geometric series. Notice the restriction that R is not equal to 1. Obviously we can't have 0 in the denominator, and if R was equal to 1 we would have 0. Now what does that mean? If we have R equals 1, our original series would be 1 plus 1 plus 1 plus 1 and so on if we let A equal 1. And that is a trivial case anyway. Let's do an example of that. Let's suppose we want to sum the first 10 terms of this geometric series. 1.5 plus 6 plus 24 and so on. The first term is 1.5, so A is 1.5. The common ratio is 4, and we can work that out by taking, let's say, 24 divided by 6. And n is 10 because we are summing 10 terms. There's the formula we're going to use, and we substitute the three values we have. And when we do and work it out, you can see that the sum will be quite a large number, 524,287.5. Let's try another one. The first 8 terms of that geometric series, negative 16 plus 8 minus 4 and so on. Again, the first term is negative 16. The common ratio is negative a half or negative 0.5, and 8 terms for the number of terms we want to sum. Substituting our formula, and in this case the sum will be negative 10.625. What about if we want to sum the terms to infinity? Does that make sense? Look at this geometric series. 1 plus 3 plus 9 plus 27 plus and so on. What if we kept adding those terms forever? well, we know a equals 1 and the common ratio is 3. Let's take partial sums. The first term is 1. Then we can add the second term to the first term, 1 plus 3, which is 4. And then the third term to the sum of the previous two terms, which is 13, and so on. What's happening to the result? You can see that we are getting results that are getting larger and larger. We have 1, 4, 13, 40, and so on. In other words, as the number of terms summed increases, the sum increases. It's unbounded. But what about for this one? 64 plus 16 plus 4 plus 1, and so on. The first term is 64. The common ratio is a quarter. Let's take partial sums again. The first partial sum is 64. The second one is 80. The third one is 84. The fourth one is 85. The fifth one is 85 and a quarter. Can you see what's happening? They seem to have more or less slowed down, or they seem to be converging to a given value. So for this example, as the number of terms increases, the sum seems to be converging to a particular value. We can show that as a graph. Plotting those points with the number of terms on the horizontal axis and the partial sums on the vertical, you can see that very quickly the values seem to become very close to something just above 85, almost an asymptotic sort of behavior. Let's see if we can obtain a formula for the sum of an infinite number of terms of a geometric series. This is the formula for the sum of the terms that we've used previously. What happens if we choose values for the common ratio that are between -1 and +1, and when we let n become larger and larger? Then r to the power of n becomes smaller and smaller. Let's see why. Let's suppose we choose r equals 0.1 and n equals 1. Then r to the power of n becomes 0.1. If we choose the same value for r, but this time use n equals 5 and then n equals 10, you can see that r to the power of n becomes very small indeed. So, in that case, we can say that for large values of n, in other words, as n approaches infinity, and for values of r between -1 and +1, the power of r to the power of n term, becomes very, very small, negligible, so we can leave it out of the expression. So we have that s of n approaches, as you can see there, a bracket 1 minus r to the power of n, which we will let approach 0, over 1 minus r. And we can write that as s subscript infinity. That means the sum of an infinite number of terms equals a over 1 minus r. We'll work out the infinite sum of this sequence: 100, 25, 12.5, and so on. The first term is 100. The common ratio is 0.25. If we substitute those values into our infinite sum formula, we have a final answer of about 133.33. What about this one? The first term is 1. The common ratio is -0.2. Substitute and we obtain a value of about 0.833 for the infinite sum. Recurring decimals, what are they? A recurring decimal is a decimal that has a recurring number of digits that go on basically forever, like the example that you can see, 0.333333, and so on. Can we write recurring decimals as fractions? Yes, we can. We can split it up to create an infinite geometric series. 0.3 plus 0.03 plus, and so on. And then we can apply our infinite sum formula. In this case, the first term is 0.3, the common ratio is 0.1. Our infinite sum formula becomes, for these values, 3 over 9. So 0.333 and so on as a fraction is 3 over 9. And I won't simplify that to a third because we need to remember that for what will happen in a short time. Let's suppose we want to write this recurring decimal as a fraction. You can see that we have two digits repeating, 1 and 3. We can split it up into an infinite geometric series. This time the first term is 0.13, the common ratio is 0.01. Making the substitution, the infinite sum becomes 13 over 99. Do you notice anything so far about our two answers? The first example that we've done, our answer was 3 over 9. The second example, our answer is 13 over 99. Do you notice what is in the numerator in comparison to what we started with, and what sort of numbers are in the denominator? Here are some that I haven't shown you, but these are the answers. 0.123123 and so on as a fraction is 123 over 999. Here's a longer one. So what's happening? Can you predict the answer to this one as a decimal? We can see that the answer will consist of the numerator repeating. And the numerator repeating becomes, as you can see there, 0.58316, and those 5 digits repeat to infinity. I hope you've enjoyed this presentation of geometric sequences and series, and I hope I will see you soon for some other great videos. Bye bye.